I'd like to thank all of you for showing up today. It's very nice to talk to a full room. And thanks especially to my committee members, Dr. Kuyo, Dr. Rao, Dr. Dasbak, and of course Mark. It's been a really excellent experience working with Mark. He's been a source of support, both research-wise and funding. He's also been an excellent collaborator and source of inspiration, whether it be in terms of ideas for projects or specific ideas about solving specific problems in our projects. So it all comes to culmination now. As is customary for at least our group, we always start with a timeline slide. And I joined in 2017 in the fall. I finished my qualifying exam and general exam in my first 2 years. The general exam, for those who don't know. Oh, and I should also say thank you to everyone on Zoom who's joined in. It's nice to have you here virtually, and I'm glad that some of you are up at ungodly hours watching my defense. So the general exam, for those who don't know, is a PhD proposal or a thesis proposal where you present certain aspects of your work from your beginning to the general exam, and more importantly, an idea or a roadmap of what you would expect to do in the years following that. And of course, I've been doing research for about 2.5 years after that, and it ends with the thesis defense. Yeah. So I'm going to list out the projects that I did during my PhD. On this slide, I just have 2 projects, and these are 2 projects that are done just with Mark. We essentially worked on this in 2020, a mix of meetings on Zoom and lots of email contact because Mark was on sabbatical in California. The first paper, and the reason these 2 papers are on this slide is because they form the bulk of my thesis, and I basically called upon the results of these 2 papers to form the content of my thesis. What I will be talking about pretty much exclusively today are some results from the first paper, and the title is a bit vague because I think it was an ambitious project to connect various things in quantum information. And so instead, all I'll say is that I'm going to focus on explicitly the part that is limits on quantum channel estimation. And that's the part of that paper that I'm going to talk about today. So other projects I worked on during my PhD are the following. Some of them are done just with Mark, some done with collaborators, and these are here just for completeness. I'm not going to talk about these projects today. So I thought to start with this funny graphic. This is what I ended my general exam presentation with. I drew up this thing because I came up with some ideas for projects that I might do from that time until now. And it was ambitious, and I had a vague sense that these things that I've written here would be connected in some way, and they are connected in some way, but I didn't get a chance to work on every single one of these topics. What I have ended up working on, what I will talk about today, is the one on the top. The letters QFI stand for quantum fission information, which I will explain in more detail in the next 30 or 40 minutes. And that is the most important quantity, or the most important expression in what's called metrology or quantum estimation theory. Metrology is just a word for the science of measuring things. And what we did in our project is use this to place limits on metrology, and also we showed how it can be considered as an information measure in quantum information generally. So I thought it would be nice to just have it up here as, I guess, a bit of accountability, and also I had somewhat of a grand planning I ended up doing part of it. So I don't really like outline slides, and I know Mark doesn't like them either, but I thought that I would have a very brief outline just to give you a lay of the land of what I'm going to be talking about. So my aim in this talk, and the reason I put quite some effort into preparing it, is that I would like the first maybe 20 minutes or so to be accessible and to not have any excessive jargon in it. So that's going to be the first 1/3 of this talk, which is an introduction to parameter estimation, which is a fundamental task in statistics or in physics also. And then I'm going to talk about, so when I introduce parameter estimation, it's going to be in the context of parameter estimation when you have probability distributions. And then as you the framework of parameter estimation of probability distributions can be extended from the classical world to the quantum world. And when we do that, there's a sort of various rungs of a hierarchy where the first rung of generalization of probabilities is quantum states, and they can further be generalized or broadened by considering quantum channels. And so I will briefly talk about how we can generalize the scope of estimation theory, beginning with the most basic task, going to the slightly more sophisticated task. Finally, what we're actually interested in and the main results we have are fundamental limits on estimation of quantum channels. So I'm going to need to build up a lot of these things so that we can get to a point where we can state and understand this final result.
Yes, sir. If you have a question, would you like us to stop?
Yeah, sure. If you have questions, feel free to stop me. If
I don't know if Mark has a problem. I must get 3 questions.
I mean, I guess every speaker's preference is to answer. If the question is quick, you can ask it.
Fair.
If it's going to be an involved answer, which obviously you may not know, but that might take my flow. And everyone on Zoom, if you have questions, I would prefer if you just type it in the Zoom chat. Surya is monitoring that, and he will just let me know what it is. So now we begin. Consider. So I'm going to talk about parameter estimation, and in its most basic form, it's the task of when you have certain amount of data that you collected from some experiment or some observation. What you want to do is you know that there's some unknown number embedded in that data, and you want to come up with some strategy or some procedure to extract that number from the data you have. So to be more particular mathematically, the common symbol used for an unknown parameter is theta, and the data we have, you can think of it as various instances or various samples of a random variable x. So let's say you have n samples of data, they're represented by these lowercase letters. And what we assume is that each value of data affects the distribution of these samples in a particular way, and that's governed by a probability distribution. So what this means is for every theta, there's a different probability distribution. And so when you're given a certain amount of data, you know that it's governed by one of the distributions in this family, but you don't know which one. And so that's the whole. That's what you have to do in a clever way. So our goal is to obtain something called an estimator. And again, standard notation used for that is to put a hat on top of the parameter. So we want to estimate theta, and what that means is we want to obtain a number theta hat. And obviously, theta hat will not be perfect unless you have the perfect estimation scheme. And what we will show is that in most cases, most practical cases of interest, there's fundamental limits on how well you can estimate a parameter, which means just because of the fact that you have a limited amount of data at your disposal, it means that your estimate can never be perfect. What does it mean for an estimate to be perfect? Well, there's 2 aspects of, I guess, perfection when you have an estimator. These 2 concepts are accuracy and precision. And there's a general heuristic in like all of science, all of statistics, that there's a trade-off between these 2 things. And what we do and what is common in estimation theory is to assume that the estimator we have is unbiased. And unbiased is an alternate way of saying that we assume it's perfectly accurate. We assume that it's perfectly accurate in the sense that on average, our theta hat always converges to theta. And that's what this statement means. It's just a mathematical way of saying what I said in so many words. And therefore, once we assume the estimator is accurate, we kind of restrict the goodness, or we consider a good estimator to be one that's precise and a bad estimator to be one that's imprecise. So assuming accuracy, we limit our study to how precise or imprecise the estimator is. And the figure of merit, or the quantity we use to like quantify how precise an estimator is the variance, and the variance is just the square of the standard deviation. So these are equivalent figures of merit. So the first line is just a repetition of what I said. We have n samples of data, and we want to obtain an estimate or an estimator of data called theta hat. The notation here just means that we're going to use n samples of x to obtain theta hat, and arguably, or pretty much, it's accepted that the most fundamental tool in estimation theory is something called the Kramer-Rao bound. And this is something that's been known for a really long time. I think this bound was developed in the 1940s for this particular case, and it provides a lower limit on the variance of such an estimate. Why is this bound important, or why is it useful? It's because, let's say, when I showed you that we had a certain number of samples of data, to obtain an estimate of data from x1 through xn, you would have to do various you would have to do something. You might take the mean of the data, you might do various other processing, and it would also depend on, it essentially depends on the procedure used to obtain data. But the Kramer-Rao bound says that no matter what you do, no matter what procedure you use to obtain theta hat, there's a minimum amount of error that you must allow. And this is, and it's fundamental in the sense that it cannot be circumvented. It's a basic statistical property. And I'm not going to go into details, but you can also think of it as essentially coming from by invoking the law of large numbers. And the other thing you might notice is that if n goes to infinity, or if n is really large, then this term on the right is going to become smaller and smaller, which is what you might expect. If you have a lot of data, you will expect your estimate to be more and more precise. And if you have an infinite amount of data, you might even have the perfect answer. The other quantity that's important here is this I subscript f quantity, and that's called the Fisher information. I alluded to that briefly when I showed you the funny diagram where I spoke about the quantum Fisher information. This is the classical Fisher information. So I should say now that so far, whatever I've been saying about parameter estimation holds in the classical case, which means that we have not yet allowed for quantum objects or quantum states. And we will do that in following, I guess, 20-30 minutes. It's not really important for us right now to know how the Fisher information is defined or what its mathematical properties are, but I have stated this formula for it just so that I can introduce this quantity, which is the derivative of the logarithm of the probability distribution. It's known as the logarithmic derivative, and that's kind of just like saying what I just said in a different way. And the reason I'm showing this is because, as I said, we want to extend the parameter estimation theory to the quantum case. And to do so, we also have to extend the Fisher information to the quantum case. And to do that, we will see that we need to generalize, in particular, the logarithmic derivative to the case when we have quantum resources. So that's what I'm talking about now. I'm not going to go into a lot of details about what quantum states are. I will just say that there's various microscopic systems of interest which are governed by quantum mechanics and not by classical mechanics, in the sense that the tools of classical physics or the tools of classical mechanics cannot describe their behavior accurately, and therefore we need to invoke quantum theory or quantum mechanics to explain their behavior. And such systems are known as quantum systems, and their states or their behavior is described most generally by something called a density operator. The common notation for such operators is the Greek letter rho. There's also a specific case or a special case of quantum states called pure states, which are in many cases sufficient and of more practical interest than the general quantum states. But here we are going to develop a theory that holds for all of them. So earlier we had a family of probability distributions. That is, each theta defined a distribution p theta. Instead, in a quantum setting, we don't have distributions, we have quantum states. And each value of theta defines its own rho theta. So we have a family of rho thetas, and depending on the parameter that you can think of estimation as somebody giving you some rho theta that when somebody picks a theta and gives you a rho theta, whereas where you don't know it. So you can get any rho theta that's part of this family. And the other thing I mentioned earlier is that we have n samples of data, that is x1 through xn. In the quantum case, that corresponds to having n copies of the quantum state. So it's almost, you can think of it as each row data being a quantum system that's given to it some box, and you have n of these boxes that you can use to derive an estimate of data. So what I said earlier is we want to generalize everything that we develop in classical estimation to the case of quantum estimation. So one of the most, I guess the first thing we would like to do is to generalize the Fisher information to the quantum case. And as I said earlier, we had the quantity of, one of the quantities of interest was this thing called the logarithmic derivative. We need to generalize that to the quantum case. And this is where things get slightly more complicated, and the theory also gets richer in the sense that, as I said earlier, quantum states are operators, or they can be equivalently represented as matrices. And that means that the logarithmic derivative too is an operator, or it's a matrix rather than just a function. There's actually an infinite number of ways you can define such a logarithmic derivative operator. That comes from the fact that objects in quantum mechanics don't commute in general. So all we want is that we would like a quantum Fisher information or a logarithmic derivative operator that's consistent with the classical case, and we find that there's an infinite number of ways to do that. We're not going to talk about an infinite number of ways to do it. We're just going to talk about two methods of interest to us, which we will use in the rest of this talk or in most of our work, which are denoted by the SLD and the RLD. So the SLD is called the symmetric logarithmic derivative, and the name is kind of obvious because in this equation you can see that you have these two terms which are I don't know. It's just a nice name. It's a symmetrized expression. And the right logarithmic derivative is when the operator only multiplies your quantum state from the right, and that's why it's called the right logarithmic derivative. The reason why we focus only on these two is because in some sense they are extremes of the possible generalizations of the logarithmic derivative. If you consider, so what we can do is we can define Fisher information, quantum Fisher information analogous to L theta and analogous to R theta. And the way we do that is as follows. And I'll just get into the details in a bit, but the reason we focus only on these two is that for quantum states, you can prove that this is the smallest possible quantum Fisher information, and this is the largest possible quantum Fisher. So every other quantum generalization of this quantity is going to lie between these two numbers.
Wasn't it Pets who proved that?
I think so.
Monotone metrics.
That's right. So actually what Mark is referring to is the fact that this was proved, I think in 1996 or 2001, something like that. And the way it's proved is by connecting the quantum Fisher information to distance measures in quantum information. So you can connect each of these to a certain distance measure, and you can show that they have a certain relation, and that relation is inherited by these quantities. We do like go into a lot of this in our longer paper that I'm deriving this talk from, but I'm not going to talk about it right now. Just for those who are not familiar, the operation called TR is short for trace, and it's a common matrix operation. So so for any operators, you can define such a trace operation. You can also multiply operators together, and that's how we get these certain quantities. I will mention that there's a small caveat. These formulae hold when certain conditions are met, and if those conditions are not met, the quantities are infinite. So we call those conditions as finiteness conditions. It would have been nice to provide them for completeness, but I think again, just in the interest of simplicity, I haven't written them down over here. And actually, in a vast majority of cases, those conditions don't even kick in. So what I had a few slides ago was this Kramer bound over here, and this is the bound that I had for the classical case. You can see that the letters P and rho look similar, but P is a probability distribution, This is the bound we had earlier, and what we find is using the two Fisher information quantities that I defined in the previous slide, we can have bounds that look very much similar to the classical bound, and that's what we were going after. You can use the SMB Fisher information or the RLD Fisher information to derive such a bound. One thing we notice is, or one thing that we're interested in, is to see how this right-hand side scales with the number n, which is the number of samples you have, or the number or the amount of data you have. And in all of these cases, we see that the variance cannot scale better than 1 over n. And since these bounds are like fundamental statistical bounds that are independent of your experimental procedure, it means that you cannot ever circumvent that scale. And, however, we know that in certain quantum or in certain estimation tasks, certain specific estimation tasks, we can do better than 1 over n. And that is obviously something that's very interesting and intriguing, because if we can identify the tasks in which we can do better, we should also know how to do that. I'll say that again. Tasks for which the variance can scale better than 1 over n are very important to us, because we can do more with far less resources or far less data. To do so, we need to introduce the idea of quantum channels, and for certain estimation tasks involving quantum channels, the variance can be made to scale as 1 over n squared. This is often denoted in the quantum information or quantum metrology community as Heisenberg scaling. The reason for that, I'll explain just very briefly, is that it reminds us, or the form of the scaling reminds us of the Heisenberg uncertainty principle. And this is just a repetition of the line I had in the outline slide. So what we've done so far is develop estimation theory for probabilities, extended it to states, and now we're going to extend it to channels and show how we can attain fundamental limits, or how we can attain this new limit of 1 over n squared. So a brief introduction to quantum channels. As I said, quantum channels are like the next rung in the hierarchy from quantum states. So they are, instead of static objects or descriptions of systems, they are dynamic objects that convert one quantum state to another quantum state. That is, this notation n going from A to B means that n is a symbol for the channel. It accepts a quantum state in system A and converts it into a quantum state on system B. And that's kind of what we have with this symbolic notation. Why are quantum channels interesting? It's because, first of all, we're always interested in how systems evolve or how the dynamics go. And also, the framework of quantum channels describes basically any possible evolution that's allowed by the linearity of quantum mechanics. Now, earlier we had families of probability distributions, and then we had families of quantum states. We're going to extend that by considering a family of quantum channels. So again, we have different data, and each data defines a different channel. So the goal, analogous to what we had earlier, is to estimate a single parameter of data that's embedded in the channel. And where this differs from the classical case and the case of quantum states is that having n copies of data is not the same as having them in n different boxes at the same time. Since these channels are dynamic objects, you can instead arrange them in such a way that you get the data in a sequential manner. This schematic describes the most general way you can process a channel if you're allowed to use it n times. So there's going to be n boxes of n data, and the goal is to finally get a theta hat. Let's go back to say that. So here, when we had n copies of a quantum state, I used this notation, and I said it's analogous to having them in n something, having n boxes, each with row theta. And I just want to emphasize that having it in this form is a far more general way of possessing or creating experimental data. Since this is an adaptive protocol where you can actually apply some feedback one after the other to kind of make your protocol perform better than it would than having everything at once. So we had defined the SLD Fisher information and RLD Fisher information for quantum states. This is a very standard way of extending these definitions to quantum channels. So if you look at this previous slide, you can see that there's a quantum state that's input to the channel and a certain state at the output. So what we do is we allow for some input states to the quantum channel, and then we optimize over all such input states to get the analogous quantity for a channel. I'm not going to dwell too much on this. These are just the standard ways to define, to extend quantities for quantum states to quantum channels. What we're actually interested in and kind of the line of attack we have is to consider or to ask the question, if we allow for a catalyst or some sort of additional resource, can we get more Fisher information, or can we get more information about the parameter than without the catalyst? To do so, we introduced this quantity called the amortized Fisher information, and we're inspired to do this by a certain quantity called the amortized channel divergence that was introduced by Mark and other co-authors, I think, in 2018. What this quantity allows us to do, and I will define it in the next slide, is it allows us to consider a catalyst, and then it also requires us to subtract off the cost of the catalyst, which is why it gets its name amortized. That's why the concept is called amortization. So I just repeated this slide, this figure, just to say that such a quantity is useful because you can consider that. Actually, I'll save that explanation for later. So as I said, the amortized Fisher information is the reason we define it is because we're inspired by the amortized channel divergence. The amortized channel divergence, which was studied in this work, is found its use in estimating, or not estimating, in analyzing the power of sequential protocols like the one in this slide. And in that paper, this channel divergence was used to study the power of sequential protocols in tasks called channel discrimination. And that's what we kind of extend in some sense to channel estimation. So this formula is a bit of a mouthful, but I'm going to try to walk you through it. So first of all, we have Fisher information quantities IF. This I is a boldface I, and the reason I use that is because that denotes a quantity called the generalized Fisher information, which is a large class of Fisher information quantities, of which the SLD and RLD Fisher information are particular cases, which means that such a quantity can be defined for both the SLD and the RLD case. The symbol, the curly A, corresponds to the fact that it's been amortized. So what is the amortized Fisher information of such a channel? What I said earlier is that it allows us to consider a catalyst state while also subtracting off the cost of the catalyst state. And the letter SUP means supremum, which means we're allowing to optimize over all possible catalyst states. So the amortized Fisher information is, in simple words, the maximum gain that a catalyst can provide to this channel. And that's why this quantity is useful in studying the power of catalysis in estimation, or more specifically in sequential estimation. In all amortized quantities, there's a direct inequality that we can prove. And in words, that just means that a catalyst cannot reduce the Fisher information. And that's kind of obvious in the sense that if you have a catalyst, you can do no worse than without one. In mathematical terms, it means that the amortized Fisher information is always going to be, or rather, it can never be less than the Fisher information itself. Again, the bold script I means that this is going to hold for both the SLD case and the RLD case. It's very common in information theory to prove equalities by proving inequalities going in both directions. So if you wanted to prove that A is equal to B, it's very common to show that A cannot be less than B and that B cannot be less than A. So in a similar spirit, we always have this inequality. In certain cases, we can prove the reverse inequality. And if we have both of those inequalities holding for a certain Fisher information, have equality. This equality is what is known as an amortization collapse, and that terminology again was introduced in that paper of Mark and others. Why is an amortization collapse important? So I tried to come up with this schematic to show what an amortization collapse means and how it applies to sequential estimation protocols. So what I've done is I've cut a part of that sequential estimation protocol that I showed over here. So I basically cut out this part of it just to illustrate this point. That's this figure of the top. Now, this is what we call a two-round strategy or a two-round protocol because it uses the channel 2 times, and it has its own certain Fisher information. Let's say that Fisher information undergoes an amortization collapse. And I said that for certain cases, this can be shown. An amortization collapse means that this diagram kind of breaks up into two parts. And it means that, again, to use like an English phrase, this two-round protocol is the same as the sum of its parts. That's exactly what I'm trying to show over here. It's not, I don't think this is a very, I actually think it is an accurate mathematical statement, but this is mostly just to illustrate what an amortization collapse implies in this. We can generalize this particular. Yep.
So this is just the parallel strategy.
That's right. So Surya asked whether this kind of breakdown would result in what's called a parallel strategy. And that's right. I'll just elaborate a bit. A parallel strategy is a subset of such a sequential strategy. And what it means is that instead of having these n data one after the other, they all happen at once at the same time. And you process the results of those together. And Surya is right. So what his question implies is that the Fisher information of this two-round protocol can be achieved by a sequential protocol, but it can also be achieved just as well by a parallel protocol. So to generalize what I had in the previous slide, again, I'm just repeating that same figure of the n-round sequential protocol. If there's an amortization collapse for the Fisher information that governs this quantity, this corresponds to just having n copies of the channel in parallel. This is a powerful result because in general, if you were to compute the Fisher information of this large object, you would have to optimize over all of these intermediate things that you have control over. But you would have to optimize over all possible estimation strategies. So the things that are in the experimentalist's control are the initial state rho, these interleaving channels S1, S2, and so on, and also the final measurement lambda.
You've done this optimization on the server in our lab.
That's true.
And you can only do like what, 4 channels?
That's true. For another project with Mark about a different channel distinguishability task, we actually tried to optimize over this, and we found that we could only go up to 4 channel uses before our group server just ran out of memory. In this case, it simplifies the computation or the calculation, whether you're doing it on paper or on a computer in a very large way. And that's why it's very important result. It's very pleasing theoretically because it implies certain things about the Fisher information itself. But it also is very, it makes our results amenable to direct experimental application. So I'm just going to, I'll talk about that a few slides.
Yeah, just to make sure I understand.
Yep.
Our Fisher collapse happens whenever that is true. When it comes to the same.
I think it's, yeah, so it's like it goes both ways.
But my question is, when do you know that is true?
So as I said, there's an infinite number of quantum Fisher information. And for certain Fisher information quantities in question, we can prove an amortization collapse. That is, we can prove the reverse inequality. So our goal is to find Fisher quantities for which we can prove this reverse. And then we
It can also happen for particular channels.
Right. So the question is, if I give you a channel, I don't need to characterize it. How do you know if that applies or not?
it's so there's a few like I guess subtleties here. One of them,
What about RLD Fisher?
yeah, that's what I was thinking.
Oh, sorry.
So it depends on the Fisher you're considering. So one of the results I'll show at the end of the talk is that for the RLD Fisher information, this sort of collapse always occurs,
No matter what the channel is.
no matter what the channel is. So it means that if you consider your figure of merit as the RLD Fisher information, you can assume this simplification no matter what. And if you let's say you have the SLD Fisher information, we prove that such a collapse happens if the channels are what's called classical quantum. That is, if they have classical input and quantum output. But
Or also if it's the square root of SLD, right?
right. So that's the third thing we prove, that if your figure of merit is not the SLD Fisher information, but rather its square root, then such a collapse holds for any channel. So
my other question is about the SLDR and is the choice to use one or the other, or there is one which is better.
So
Good question.
it is a good question. If you are estimating a single parameter, as I said, this quantity is always less than this quantity. What that means is that this bound is always tighter than this material. So if you're estimating a single parameter, you will probably never consider the RLD Fisher. And but that what I just said holds when you have quantum state.
But it could be useful for channels.
That's it. So for channels,
Since you have the amortization.
yeah. So I was just going to say that if you restrict to quantum states and a single parameter, then you don't need to care about the RLD quantity. If you can evaluate the SLD quantity, that's the one you can care about because it's the smallest one, and so it gives you the tightest one. And also, there's theoretical results that show that it's achievable in large numbers. So if in that restricted case, that's the only one you would care about. In the channel case, because it's hard to optimize over such a sequential strategy, we are interested in quantities that have an amortization. Therefore, the RLD quantity might be that's it.
Maybe say something. Are you going to say about how to compute it for a channel?
I'm just going to mention it.
Oh, okay.
Here comes, so I just wait. So, just to get back, what I was talking about is an amortization collapse, where we want to find the quantities for which such a collapse occurs. And as you might have heard in our conversation here, this occurs for two quantities. It occurs for the RLD Fisher information for all quantum channels. It also occurs for the square root of the SLD Fisher information for all quantum channels. But I shouldn't say these are the only ones it occurs for. These are the ones we prove. How do we do that? We do that by proving certain technical results called a chain rule. And we prove two different chain rules. So we prove a chain rule for the square root of the SLD Fisher information. We also prove an analogous chain rule, so it's got the same terms, except the quantity is the RLD Fisher information. I'm not going to go into much details about how to understand this quantity, but I will show how, if we have such an inequality, how it leads pretty straightforwardly to an amortization.
Why do you call it chain rule?
I think it's called a chain rule. I can just invoke this in the sense that if a chain rule holds, this entire thing kind of simplifies.
I think it's just that, like, the expression on the left is a composition of rho theta and net theta, and then that's like the chaining of those together and break it down.
Right. Yeah. I don't. Yeah.
I think it came about also from what's called chain rule and information theory.
Okay.
Right? Anyway, please continue.
Just to repeat, Mark asked why it's called chain rule. I don't think I had a good answer. I don't think I have a good answer right now. And Mark mentioned that it might come from previous chain rules in what I want to show is how a chain rule results pretty straightforwardly in basically 3 lines of algebra to an amortization collapse. So what I'm going to use is the second equation in this box, which is the chain rule for the RL information. So this is the same inequality that I had in the previous slide. This can be rewritten as follows, where all we're doing is we're taking this term and bringing it to the left hand side. This is exactly the expression we had when defining the amortized Vishal Katariya, where we're allowing for a catalyst, we're subtracting the value of the catalyst. So what we do is to get back to the amortized Vishal information, we have to optimize over all of the input states or all of the catalyst states. So if we optimize over all catalyst states on the left hand side, that expression is actually the exact same as the amortized RL Vishal information. That's what we get. What we have now is that the amortized Vishal information is less than the Vishal information itself. And I said earlier that if we can prove this inequality, which is like the reverse of the obvious inequality, we have equality. And that's exactly what we get. We get that the amortized RL Vishal information is the same as the RL Vishal information itself. In words, since I've been using the word catalyst, it means that catalysis cannot help to increase the RL Vishal information. And since I have this diagram, and since Surya mentioned parallel protocols, it means that to maximize the maximum RLE information you can get from such a protocol is the same as the maximum RLE information you can get from a parallel protocol, which is much simpler to do and also much simpler to calculation. Right. So, I think I'm doing okay. The next thing we do is once we have the chain rule, which we showed is the same as having an amortization collapse, we are finally in a position to state Kramer-Rao bounds, which we talked about long ago, for channel estimation. So we use both of the chain rules that I showed in this slide to obtain 2 different Kramer-Rao bounds, and we can draw 2 different conclusions from each of those. The first chain rule we prove is for the square root of the SL information, and what it shows us is that there's the following lower bound on the variance of any estimate data. You can see that the biggest change from the previous Kramer-Rao bounds is that we have recovered what we desired, which is the variance can be made to scale as 1 over n squared rather than 1 over n. And that's what I've said. This provides an alternate way. So the context for that is that we already know that in various estimation tasks, such a scaling is possible or such a scaling is attainable. Our technique using the chain rule provides an alternate way to understand how this comes about. And it also is the ultimate limit to how low you can get the variance when using a sequential protocol. So here we've shown how Heisenberg scaling or how 1 over n square scaling can arise. The next thing we're going to show is how to use the chain rule for the RL information to get a different Kramer-Rao bound. You can see here where the Fisher information in question has the hat, so it's the RL quantity. And the reason why we had an n square in the previous slide is because there was a square root in it. In this case, there's no square root, and so the variance can scale only as 1 over n. What this means is that in most cases of practical interest, the variance will only be able to scale as 1 over n. And by most situations of practical interest, I mean that whenever this quantity is finite, then the variance can at best scale as 1 over n. And that's actually true in most of the cases, and actually all of the cases where experiments have been proposed or designed to attain the Heisenberg limit. The RL Fisher information in those cases has been different. So whenever the RL Fisher information is finite, that means that Heisenberg scaling is not possible or not attainable. And so this Kramer-Rao bound, not only is it a bound on the variance of an estimator, but it's also a no-go condition for Heisenberg scaling.
Can you give us examples of channels for which, maybe it'll come later on, but examples of channels for which, the RLD is infinite versus finite?
Yeah.
Yeah.
So I can use the board.
Yeah.
So in general, we have in the most general case, we have families of channels defined as this, which is exactly what's over there. There's a subset of channels called unitary channels. And they are special in the sense that if you have a pure state and you send it through a unitary channel, say U, or let's say U theta, you get another pure state. And whenever you have a unitary channel, the RLE Fisher equation is infinite. And what that means is for such channels, this bound actually makes no sense because this number is infinity. And so this the right hand side is basically zero. So the bound basically says your variance is bigger than zero, and that does not mean anything. So
Can you make it a little more concrete? Like there's usually like a Hamiltonian.
Yeah.
Like,
So unitary channels can be represented as follows, where if you start with the state rho and you apply a certain data, it means that mathematically speaking, what happens is that the rho gets sandwiched by two different exponentials, which are like
Theta's time.
data can be anything.
I guess if it is time, the minus signs will be flipped.
Yeah, I actually don't know what the correct minus sign notation is here. So, such channels always. So if this rho was a pure state, which I didn't say much about, but I did say that there are special class of quantum states. If rho is a pure state, then this whole state is also pure. And really, the result we invoke is that the RLE Fisher equation of pure states is infinite. That's equivalent to saying that the RLE Fisher equation of unitary channels is infinite.
And then what about when RLD is finite? For example.
Okay, sure. So the simplest example to take for considering RLD of a channel that has finite RLD Fisher equation is to just consider a unitary channel with like a small amount of noise added. And in all of those cases, the RLD Fisher equation is finite. I'm just going to use that opportunity to say that most experiments do have noise or do have some error in them. And
Oh.
And so an alternate way of thinking of this bound is whenever there's a small amount of error in the estimation protocol, Heisenberg scaling is not possible. I think the answer Mark was looking for was something more concrete. So we study a channel in our paper called So there's a channel called the amplitude damping channel, which describes a certain type of noise. And then there's a generalized amplitude damping channel. The reason I'm saying this right now is I'm not talking about it in this talk, but it's in our paper, in the two papers that I mentioned at the beginning, we actually evaluate these bounds for this particular channel. For this particular channel, the Fisher equation is finite, so these bounds actually do make sense. And yeah, we value them. The generalized amplitude damping channel has two parameters, gamma. So to be specific, in the example we consider, we're trying to consider tasks where we're trying to estimate gamma or n, or in the case of multiple parameters, we're actually trying to estimate them simultaneously. So finally, I just stated two Kramer-Rao bounds that we obtained, and I just want to state some desirable characteristics or properties of these bounds. The first one is that they apply universally. What does that mean? First of all, they apply to all quantum channels. And as I said earlier, quantum channels or the framework of quantum channels encompasses all permissible quantum dynamics. So they apply to pretty much any interaction that's allowed by quantum mechanics. Second of all, our bounds apply to these sequential protocols or sequential strategies, which are also the most general, which describe the most general way of using or processing n copies of a channel. So in both of those senses, our bounds apply in a universal manner. Our bounds are single letter, which is a term that comes from information theory. Simplest way to understand that is by considering such an amortization collapse. It means that to actually compute the RLD or the SLD Fisher information of this quantity, instead of optimizing over all of these and optimizing over n uses of the channel, we actually have to only compute it for one use of the channel. And that's what single letter means. So single letter is due to the chain rule and the amortization collapse. Obviously, this makes the bound easy to compute, or I should say easy it works. It makes it easier to compute. And lastly, relatively, our bounds or the quantities, the right-hand side of our bounds can be computed by a Bayes optimization formula. We provide these formulae in our papers. They're also in my thesis, but in the interest of time, I did not include them today. In particular, the RLD Fisher information here can be computed by what's called a semi-definite program, which can be solved in polynomial.
So the SLB,
it's a bilinear.
Then Zhao, Gail, was like an SDK somehow.
Yeah, she does. I don't fully. I didn't work with that. The last thing is just a repetition of what I said. That this is the RLD Fisher information based Kramer-Rao bound. If this quantity is finite, as I said, then Heisenberg scaling is unattainable. And finally, I'm actually going to explicitly write down the finiteness condition of the RLD Fisher information. The reason I didn't introduce it earlier is because I introduced another symbol, gamma. Gamma is what's known as the Choi operator of a channel. And I'm not going to talk in detail about what or how to interpret this finiteness condition. All I would like to say is that if the finiteness condition is met, then Heisenberg scaling cannot happen. So I'm just going to conclude by saying that these are the results that I spoke about today. We define the amortized Fisher information of quantum channels. The reason we do so is to study sequential estimation protocols. We then prove chain rules for the square root of the SLD Fisher information and for the RLD Fisher information. We showed how chain rules lead to amortization collapses, both like mathematically and kind of graphically. And I didn't show how we do it, but we use the amortization collapse to get Kramer-Rao bounds, which are single letter and therefore desirable. Finally, corollary or like side effect of that itself is that if the RLD Fisher information is finite, then Heisenberg scaling is finite. I think I have a slide with some possible future directions, which I will just state very briefly. And these are things that Mark and I spoke about while working on our project, but we figured that what we did constituted its own like complete body of work. So the first thing we spoke about is to incorporate energy constraints into the framework of estimation, which means that we have a certain input quantum state, and as of now, we allow it to be any possible state. It makes sense physically to impose some constraint on its energy, and if we do so, we would kind of further the scope of our estimation protocol, because you can think of our current results as applying to having an energy constraint, but that constraint being infinite. Finally, we showed this line. We showed that if the RLD Fisher information is finite, Heisenberg scaling is unattainable. But I don't think it's very clear to us right now if we can show the reverse. So we know that this is a necessary condition for this, but we don't know if it's a sufficient condition. So that might be an interesting thing to prove or to prove. And finally, since we focus a lot in our work on the RLD information, one thing we would like to do, which is very desirable, like information theory in general, is to apply or is to find operational meanings for these quantities. So a paper by KJ Matsumoto in 2005 spoke about the operational meaning of the RLD information for quantum states, and it would be nice if we can generalize their interpretation with their results to quantum channels. Just to give the possibility of any questions. That.
Stand right here. I think.
Oh.
Question. Oh, okay. Okay. Yeah.
Yes, thank you, Vishal. So it was very clear. I have just one question. So my understanding is when it comes to official information of states, the Heisenberg scaling is technical, but for channels, if I'm understanding correctly, you're saying that most of the access it's going to be unattainable. So do you personally see like some sort of a conflict? Because in some sense, wouldn't you say that the channel should generalize the results of that for the state? That's how I was thinking. I don't know.
Yeah, I think so. What Ashok is saying is that if you have a family of pure states, then Heisenberg scaling is possible.
Channels.
In some cases. But
I don't think it is possible.
yeah,
right?
so the thing is,
The first thing you said was that it's not possible.
right, so there's two ways to think about it. One is that it's possible if you have pure states that are with entanglement. And the other, so this is one way to attain Heisenberg scaling. The other
But
way,
even with that, it's still not possible because you're talking about n copies of that state, right? One of the first slides you showed.
okay, that's
So it's only for like unitary channels, right?
actually, yeah, you're right. So let me, I leave this here, but this is not exactly correct. So there's certain cases where people say Heisenberg scaling is possible for cases when you have pure states, but actually that Heisenberg scaling is not with respect to the number of states, it's actually with respect to a different quantity. So one particular example is like if you do interferometry and you have known states, so known states are I'll just say that it's a certain state that's characterized by number n. You can show that the Fisher information.
You have to mention John Dallas.
So I mentioned, so there's these things called known states. And known states were invented or were popularized in quantum metrology by Professor John Darwin, who was part of our group for a long time and passed away last year. So that's why we, like in our group, I guess we always said we will have a fondness for known states. So if you have known states for like some type of interferometry, you can show that the Fisher information goes as n squared. And this is often interpreted by the authors as Heisenberg scaling, but it's n squared where n is a property of the state. It's not the number of those states. So if you're considering Heisenberg scaling with respect to the number of states you have, you must have unit numbers. You cannot just have your states.
Just I think I understand.
So then for a unitary channel, what kind of strategy would you use to achieve Heisenberg scaling?
You can use some. I think you would do something like a parallel strategy like this.
Yeah. Kind of just looking for one word.
Oh. like an entangled strategy. You would have an input state that has a highly entangled input. And then if with a suitably chosen measurement, you would get
So like some kind of GHD state, right?
Okay, so that's what I wanted to ask as well, actually, that's the.
So this is why we need to generalize the theory to have energy constraints also, right?
Right.
Because then we'll capture both the number and the energy.
right.
So, okay, so I'm not an expert on this, so correct me if I'm wrong, but my understanding is if you have an initially entangled state, I don't think it matters in smooth states. As long as you start with entangled one, apply this strategy, you should end up having a Heisenberg state. Now, if I'm wrong, please tell us that I'm wrong. That would be nice. But my understanding is you only the moon states. The n in that case will be just the number of entangled systems. Fine, if I remember.
What do you mean by number of entangled systems? Like
Let's say you start with A1 to AN, and instead of doing the
Oh.
product state, right, in the beginning,
that's what would happen over here.
right, okay. I guess what I'm
Because-
saying is, my understanding is that this is a more general, so it doesn't have to be the n from the moon state.
Exactly.
It can be the n as in the number of systems.
Right.
Okay, so if that's the case, we should expect that there should be some what's the word, like consistency between the fact that you're getting the Heisenberg scale when you have states, but when you have channels, you're not getting the Heisenberg scale. Should there be some sort of a
Well, so unity channels basically they take pure states to pure states, so there's no error in them. If I was to add like a bit of noise here, then the Heisenberg scaling would collapse. So in this it holds for purely unitary channels. But if the channel is unitary with zero noise, you can attain Heisenberg scaling. Once you add even tiny amounts of noise, it collapses.
I see. So I see. So the optimal strategy where you're attaining the Heisenberg scaling is one where you have unitary, and that's why.
Right. Because there's no noise.
Okay. I think I see what you're saying. One last thing, the channel, sorry, the state you're optimizing for, it's generally entangled. When you're coming
In this
to
case?
efficient formation of channels,
Yes.
it is generally entangled, right? Just
Yeah. So here you're optimizing over pure states over not only system A but you have
right. Okay, I think it's perfect. Thank you.
Any other questions from the? Are there any questions that the committee members would like to ask in front of everyone, or you can also wait for the private discussion?
Maybe one is you made a point about this amplitude damping. That's a specific case. Of course, the contrast would be only a phase damping. So in physics terms, does it mean dissipation? Always there's some kind of dissipation, not just before it's that's how I understand it. There's even a slight dissipation. Then these things.
That's right. So if I go back to this finiteness condition, so how do I explain this? The support of an operator is like the part of it where, or the part of the matrix where its entries are non-zero in a vague way. So once you add noise, or like not just decoherence, but different types of noise, your matrix in general has lots of non-zero elements, and that's kind of what makes the collapse happen. So it can happen for different types of.
I think it's fine to say full rank.
Right. That's what's So once the Choi operator of the channel becomes full rank, this holds regardless of the noise. That is true for various common noise.
As a matter of fact, any realistic channel equation has Heisenberg.
Well, that's what we show, but I think there's also some work going on right now about how to do some sort of connection to kind of contain the hyperbole scaling?
I'm not.
We should clarify that a lot of this theory is, I mean, we're kind of exclusively finite dimensional case, right? We didn't develop theory for Masonic channels, so I think there's more to see.
Issue that having more degrees of freedom between unity, improve things rather than.
Possibly. I mean, it depends on the channel. Like, it's just a pure loss channel, and I would say Heisenberg might still be possible. Right? Like, if it were just an amplitude mapping channel, that Choi matrix does not have full support. It's generalized. And there might be more refinements of Kramer now. Like a finite sample.
Oh, okay.
Yes.
One more question.
If I may ask, yeah. So could you go back to the definition of amortized vision? I think, okay, so I'm trying to understand, so I guess I understand the efficient information of channels and efficient information of states. But is there a way of understanding the efficient information of a channel that's acting on a state, both depending on the parameter favor? That kind of
This quantity.
yes, yes.
So I'll just repeat the question. Ashok. So Ashok is saying this this quantity is the efficient information of a state, and then previously we had defined the efficient information of a channel. But here we have the efficient information of a state that's acting on of a channel that's acting on a state, with both of them having effective data. I mean, I guess the simple way to answer that is to say that this is also a state with dependence on data. So you can invoke that same definition for the efficient information of states.
Okay, mathematically, fair enough.
Yeah.
In any,
I think it'd be helpful to go back to the diagram. Yeah. Right. So you, I mean, you want to. It's like.
So if you're so like let's say you're calculating the efficient information at this time slice, you would invoke the efficient information of this state. At this point, you have the channel having acted on the state here, and that's the efficient information that you would invoke. Now here already the state has a dependence on the parameter data.
I see, okay, okay.
So it builds up.
That makes sense, yes, that makes perfect sense. Okay.
And we should also say the efficient information first at zero.
Makes sense.
This is
There's
there's
no-
And then after that first channel, that is kind of the efficient information of the channel. Then once you start building out, that's where the amortization comes in. The channels after the state.
That makes sense. Thank you, sir.
Doctor, do you have another question?
I had another different question, and that is, for instance, in slide 20, you say that the amortization cannot change the efficient information. Now, what is then the role of catalysis? Speed up? What sense?
In the sense that
Not changing.
increase the efficient information is all we're looking for. So that's the goal of the protocol, is to, in some sense, in like qualitative words, to accumulate as much information about data as possible. And so that means to accumulate as much efficient information as possible. So
Let's say in the sequential, I mean, you said it at the top, that the sequential protocols don't come.
right. So what we want, what we are kind of looking for is for the for these channels, if they happen, if catalysis helps, then having n use of the channel in this form is going to be better than having them all at once. Because then you can have this channel use kind of increase the power of this channel, and then this channel increase the power of the next one. But we show that that doesn't happen. So if catalysis did help, then we would have that the increase with channel uses would be more than linear.
So what is the role of catalysis?
I mean that's the goal of it, and I guess it depends on the figure of merit. So if you're considering the RLD efficient version of this protocol, we know that catalysis cannot. But if you're trying to maximize, let's say, the SLD efficient version of this protocol, we cannot say that catalysis doesn't help. So in that case, catalysis may help.
Yeah, that's an interesting question to identify when it happens.
Also had another question, I think it's probably related. Your strategy of proving the equality and therefore this collapse was supposed to get the other one, going the other direction. And for RLD, it was straightforward. But for SLD, you went to the square root. Now, why square root? And you see, because I'm trying to see where the 1 over n squared I can relate to simple terms. So that seems to be the key. It's because you use that square root that is going to get the
So what Dr. Rao is asking, yeah, you're right. What Dr. Rao is asking is just to paraphrase that how do we get the n square in this count? And mostly it's because of the fact that it's due to the fact that the chain rule we prove holds for the square root of the Fisher equation. And
you prove it for some other root. Any square root.
maybe, I mean, I don't know.
Could we get it for, so you're saying for some root between
Yes,
1 and 1/2? That would be
Maybe
very
it's not 1
interesting.
over n squared, maybe it's 1 over n to the 3 half. I don't know, I'm trying to see whether there are
That's
other
interesting.
strategies.
that
This is what we could show it for. You know, it's consistent with other findings.
but it's also true that we essentially focus on the SLD and the RLD quantity. Because there's lots of other ones in between, we didn't really consider any of the other ones.
Yeah.
So it's possible that if we consider another one, a different kind of chain rule holds that's between these two.
So we should do that before you leave in January and write it down.
If I make a similar point, I'm not going to make it as a question.
It's uncommon.
So if we look, so something similar to what Dr. Rob said. So if we look at the first equation, we square both sides. I think we can interpret the right hand side as a generalized or a generalized average. They are the ones, the averages would be, let's say, P average, I think it's called, or it's called polar average or a generalized mean. I think if you look into it online, there are forms of it where, depending on the power, it can be some mean versus another one. So the long one is a regular average, right? The linear. The one on the top, I think, is P equals 1/2, if I'm not mistaken. So it's kind of like there's that kind of like a beautiful idea that it might go into a generalized average. So I don't know, maybe that's something.
Are you trying to hint that like we can interpolate between the power?
As a power average. Okay. I guess just to add that as well.
Yeah. Possible.
There are no further questions. Please take questions on Oh, there are questions on the chat.
No,
No, that's right.